Hi folks, in the first part of this lesson we're going to take a look at the questions on the first page of the investigation sheet. Okay, so the first thing they asked you to do is to recall why trigonometric functions were so useful. Okay, so hopefully you remembered that what is special about a trigonometric function is that it displays periodic behavior. Okay, now what does that mean? Well, essentially periodic means repetitive. Okay, and a little more it's actually a little more than just being repetitive. Okay, it means it repeats itself at a regular interval. Okay, now in particular, it's what we call sinusoidal functions that were particularly useful. Okay, and here we're talking about y equals sine x and y equals cos x, and they have that, wave-like pattern to them. Okay, and when we talk about sinusoidal functions, we're not just talking about these two, but we're talking about any transformations of these two functions. Okay, so what it allows us to do is it allows us to model behavior where a value alternates between a maximum and minimum value. Okay, and there's just no end to the applications which display this kind of behavior. So think about anything moving in a circular. So any circular motion is going to be modeled by a sinusoidal function. Okay, you might also have something like blood pressure. When you hear 120 over 80, this represents the maximum and minimum blood pressure that a person has. Okay, and it alternates between this max and min. Okay, another example you probably would have seen was how tides work. Okay, they alternate between a maximum minimum, and so again, sinusoidal function. Another example might be, weather patterns throughout the year. Okay, as we take average temperatures, or take the temperatures of that occur every month, we see that they, increase throughout the year, then decrease back, and then it starts over. Now, again, in some of these scenarios, okay, doesn't necessarily increase to the exact same maximum temperature in the year or the exact same minimum temperature, but again, we're talking about using them as models, okay, meaning that they give us a reasonable approximation for the values and then allow us to predict them in the future. Okay, so let's recall how these functions were actually defined, because when you think about all these examples, notice that other than perhaps the circular motion, whereas if you think of circular motion in terms of an angle that it moves, okay, none of these other ones had to do with angles, yet that's how they were originally defined. Okay, so you would have originally defined these trigonometric ratios or trigonometric functions by considering the trigonometric ratios as a point moved along a circle. Okay, and you calculated these, say, sine values at every angle as it moved along the circle. Okay. Question is when we think about our units for angles, we use 360 degrees. So the question is, where does that number come from? There's nothing really natural about splitting up a circle into 360 degrees. It might seem natural because you're so used to doing it, but there's no real physical reason to choose that number 360. And you might ask yourself, well, why not choose something easier like 100 or 1,000 or 10? Okay, why something like 360? So let's just have a little chat about that. Okay, so where this number comes from is actually from the Sumerian and Babylonian civilizations. So we're talking, probably 2500 BC. And these civilizations did not use base 10 like we do to to count. Okay, they used base 60. Okay, so meaning they would have had numbers from 1 to 59, and then they would have started over. That would have been like their 60 would have been like their 10, where now we move over to the next position. Okay, so you might ask, why didn't they just use 60 then to split up circle? Okay, so split it up into 60 units. Okay, well, it turns out 60 isn't really enough parts to split up a circle. Okay, and one way to see that, and something the Babylonians certainly spent a lot of time doing, was studying astronomy. So motion and location of stars in the sky, and the sun and the planets. And when you think that if you're observing two objects that are very far away, like two stars in the sky, you might be dealing with extremely small angles. So if that's the person there observing those two stars, you have to deal with extremely small angles. Okay, and splitting up a circle into 60 parts doesn't give you small enough angles that you want to use as your unit. Okay, so they decided to use 360. Offers much more versatility. You're splitting it up into much smaller pieces. Okay, so again, why 360? Why not 400? Why not 350? Why not 1,000? Okay, well, there's a couple of reasons that they might have done that. Okay, and one of them, think of, again, astronomy. One of the things they would have studied would have been the position of the sun in the sky throughout the year. Okay, and they came to realize that, hey, the sun repeats that pattern about once a year, and a year is about 360 days. Okay, so if you think of the motion of, or the position of the sun in the sky throughout the year, it makes sense to split it up as 1 unit per day. Okay, so in other words, 1 degree represents the change in position of the sun in the sky throughout the year each day. Okay, now what I was hoping you'd come up with, because I asked you what's nice about the number 360, okay? And 360 is a very nice number because it has a lot of factors, okay? And when I mean lots of factors, I mean whole number factors, okay? Think of just even the numbers from 1 to 10. It's perfectly divisible by 1, 2, 3, 4, 5, 6, well, not 7, but 8, 9, and 10. Okay, so when you look at the numbers from 1 to 10, it's perfectly divisible by almost all of them. Okay, and of course, if a number is perfectly divisible, it means you don't have to work with fractions. Okay, so 360 has that great characteristic that it's got lots of perfect factors. Okay, so you can divide it up many different ways without ever having to work with a fraction. Okay. But as nice as this is, and certainly you see, if you're taking physics or you've taken physics, you see that we still work in degrees, okay, and we'll work in degrees again at the very end of the calculus course later on this year. But 360 degrees is just, again, an arbitrary number. It's a very nice arbitrary number, but it doesn't really have any physical meaning with respect to the circle, okay? So many, many years later, so probably we're talking the 1700s, okay, an alternative unit was proposed to work with angles, okay, and that's what we call the radian. Okay, so on your calculator you might see a rad option or an R option where you switch your angle units, okay, and that's what it represents. It represents a radian. Okay, so how do we define a radian? Okay, so let's take a look at how this is defined. Okay, so 1 radian is defined as the angle produced. So notice this is in italics because the actual word is subtended. Okay, by an arc, which is just a section of circle whose length is equal to the radius. Okay, it's a lot of words in there. So let's try to take this apart. Okay, so first of all, okay, let's take an example here. Let me get another sheet. Okay, I'll leave this for a second. Okay, so if I've got circle, an arc is just a section of a circle. Okay, so that there would represent an arc of a circle. Oops, arc. Okay, now this arc produces an angle because if I join the edges of the arc to the center, I see that it produces the angle. Okay, so this is what we call the subtended angle. Okay, so again, arc is just a portion of the circle, and the angle that's subtended is the angle that's created when we join the ends of that arc, okay, to the center of the circle. Okay, so this is the terminology we use to define this concept of radian. Okay, so what a radian is, it's the angle produced by a very special arc. Okay, it's the arc that's exactly equal to the radius of the circle. Okay, so for this circle here, here's the radius. This arc here, if it's exactly equal to the radius, okay, will produce this angle of what we call 1 radian. Okay, so while it might seem a little complicated as a definition, it does have a physical meaning with respect to the circle. Okay, there's one problem here that I'm posing, is that I'm defining this concept of angle, okay, using the radius of the circle. So that brings up a question. Does that mean that this measure of 1 radian will change if I change the size of the circle? Okay, well, if that's the case, it's a big problem, because I want, in the same way that 1 degree represents 1 degree regardless of what I'm working with, I want 1 radian to represent the exact same angle each time. So if you sort of take a look at the picture and you think about expanding it, it might make sense intuitively that it shouldn't change. But in the next part of the investigation, that's what you're going to try to figure out. Okay? Does this definition of an angle with this unit generate the same size angle regardless of the shape of the circle or the size of the circle? Okay? So before you move on to that, the question is, why in the world are we defining this new unit, since degrees works really well? Well, unfortunately, I'm going to have to give you the answer I often give you, is we're not going to see the power of this until we get to calculus. And we're going to see that once we get to calculus, we're going to see why working with radians, okay, is definitely, without a shadow of a doubt, the preferred unit for angles. Okay, so please move on to the next page.